The morning of August 20th, 1945, at the Yokosuka Naval Arsenal, Captain Hiroshi Yamamoto stood before a captured American 75mm gun barrel laid across wooden supports in the metallurgical testing facility. The barrel had been recovered from a destroyed Sherman tank on Okinawa 3 months earlier. Yamamoto, chief of the Imperial Japanese Navy's Bureau of Ordnance Metallurgy section, had spent 15 years studying gun barrel manufacture. He had supervised the production of naval rifles for battleships and cruisers. He understood the stresses that transformed steel under repeated firing, the way heat and pressure worked against metal at the molecular level, the inevitable degradation that came with use. His assistant, Lieutenant Tanaka, had prepared the barrel for examination according to standard Japanese ordnance procedures. They had cleaned the bore, measured its dimensions at precise intervals, and prepared cross-sections for microscopic analysis. The gun had been test-fired at the American Aberdeen Proving Ground before being shipped to the Pacific Theater. The documentation recovered with the tank indicated this particular barrel had fired approximately 11,800 rounds during its service life, including both training and combat. Yamamoto could not believe the number. He read it again in the captured American maintenance log, written in neat English script by multiple tank commanders over the weapon's operational life. 11,800 rounds. The figure was impossible. Japanese 75mm guns, the Type 3 tank guns mounted in the Chi-Nu medium tanks, required barrel replacement after approximately 1,500 rounds. The Type 94 37mm guns in the Hago tanks needed new barrels after 800 to 1,000 rounds. Even Japanese naval rifles, manufactured under the strictest quality controls available to the Empire, showed significant accuracy degradation after a few hundred rounds of sustained firing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Yamamoto inserted his bore gauge into the muzzle and began taking measurements. The rifling, the spiral grooves cut into the barrel's interior to spin the projectile and give it stability in flight, should have been worn nearly smooth after 11,000 rounds. The throat, the area just forward of the chamber where the projectile first engaged the rifling, should have been eroded and enlarged by the intense heat and pressure of thousands of firings. The chamber itself, where the propellant charge detonated, should have shown stress cracks and heat damage. He withdrew the gauge and examined the readings. The bore diameter remained within factory specifications. The rifling grooves measured 4.5 millimeters deep, showing minimal wear. The lands, the raised portions between the grooves, were sharp and well-defined. The throat showed some erosion, but far less than he would have expected after even 3,000 rounds through a Japanese barrel. Yamamoto asked Tanaka to bring the microscopic analysis of the steel cross-sections. The lieutenant laid out the photographs on the examination table. Under magnification, the steel's grain structure should have shown the characteristic signs of barrel wear, crystallization from repeated thermal cycling, stress fractures propagating through the material, areas of decarburization where carbon had been burned out of the steel by hot propellant gases. The photographs showed none of this. The steel's internal structure remained remarkably uniform. The grain boundaries were tight and regular. There were no significant cracks, no areas of obvious weakness, no evidence of the thermal damage that destroyed Japanese gun barrels with such regularity. Yamamoto had examined hundreds of worn Japanese gun barrels during his career. He knew what failure looked like at the microscopic level. This American barrel, after firing nearly 8 times as many rounds as would destroy a Japanese equivalent, looked almost new. Something was fundamentally different about American metallurgy, about their manufacturing processes, about their quality control systems. The implications were staggering. If American tanks could fire 12,000 rounds before needing new barrels, while Japanese tanks needed replacements after 1,500 rounds, the sustainability gap in prolonged combat was enormous. And this was just one example. One gun barrel from one destroyed tank. How many thousands more were there? Japanese gun barrel manufacturing in 1945 was the product of decades of industrial development, stretching back to the Meiji Restoration of 1868, when Japan began its rapid modernization. The empire had learned metallurgy from European powers, particularly from British and German engineers who had been hired to establish Japan's first modern arsenals and steel mills. By the 1930s, Japan had developed a sophisticated domestic armaments industry capable of producing everything from rifles to battleship guns. The process of manufacturing a gun barrel was well understood. It began with steel, specifically high-grade steel containing carefully controlled amounts of carbon, chromium, nickel, and molybdenum. The raw steel was forged under tremendous pressure and heat, shaping it into a rough tube. The tube was then drilled and reamed to create a smooth bore of precise diameter. Rifling grooves were cut into the bore using specialized machines that could maintain tolerances measured in hundredths of a millimeter. Finally, the barrel underwent heat treatment, a critical process that determined the steel's final hardness, toughness, and resistance to wear. Japanese metallurgists understood these principles. They had studied German gun manufacturing techniques extensively, particularly the processes used by Krupp Steel Works, which produced some of the finest artillery barrels in the world. Japanese arsenals, including Yokosuka Naval Arsenal, Osaka Army Arsenal, and Kure Naval Arsenal, employed thousands of skilled workers and used modern equipment imported from Europe or manufactured domestically under license. But understanding the theory and achieving consistent results in mass production were different challenges. Gun barrel steel required specific alloying elements in precise ratios. Chromium improved hardness and resistance to corrosion. Molybdenum increased strength at high temperatures. Nickel improved toughness and prevented brittle failure. These elements had to be mixed uniformly throughout the steel, with no variations that would create weak spots. Japan's access to these critical materials was limited. The empire had almost no domestic sources of chromium, molybdenum, or nickel. These materials had to be imported, primarily from Southeast Asia after Japan's conquests in 1941 and 1942. But even with access to captured resources, the quantities available were never sufficient. Japanese metallurgists had to work with lower alloy content than they would have preferred, substituting less effective elements when possible, and simply accepting inferior performance when substitution was impossible. The heat treatment process was equally critical. After a gun barrel was shaped and rifled, it had to be heated to specific temperatures, held at those temperatures for precise durations, and then cooled at controlled rates. This process, called annealing or tempering depending on the specific temperature and cooling profile, determined the steel's internal grain structure and its mechanical properties. If done correctly, the barrel would be hard enough to resist wear, but tough enough to absorb the shock of firing without cracking. Japanese arsenals had the furnaces and equipment necessary for heat treatment, but maintaining consistent quality across thousands of barrels was difficult. Temperature control in 1940s industrial furnaces was imprecise compared to modern standards. A batch of barrels might be heated to slightly different temperatures or cooled at slightly different rates, producing variations in final quality. Some barrels would perform well, others would wear quickly or fail catastrophically during firing. Quality control procedures existed, but they were time-consuming and expensive. Each barrel could theoretically be proof-tested by firing it with overcharged ammunition to verify it could withstand maximum pressure. But this required ammunition, testing facilities, and time that became increasingly scarce as the war progressed, and Japan's industrial capacity was strained by Allied bombing and resource shortages. By 1944, Japanese gun barrel production was in crisis. The problem was not lack of knowledge or theoretical understanding. Japanese metallurgists and ordnance engineers were highly educated, many with advanced degrees from Japanese or European universities. They understood the physics of internal ballistics, the chemistry of steel alloys, and the engineering principles of gun design. The problem was industrial capacity under wartime conditions. Japan's steel production had peaked in 1943 at approximately 7.8 million tons annually. By comparison, the United States produced 80 million tons of steel that same year, more than 10 times Japan's output. This quantitative disparity was compounded by qualitative differences. American steel mills operated with abundant raw materials, reliable electric power, and modern equipment. Japanese mills struggled with material shortages, bombing damage, and aging equipment that had been pushed beyond its designed service life. The shortage of alloying elements became critical. Chromium, essential for gun barrel steel, had been imported primarily from the Philippines and New Caledonia before the war. After 1942, when American submarines began interdicting Japanese shipping lanes, deliveries became irregular and then ceased almost entirely. Japanese metallurgists responded by reducing the chromium content in gun barrel steel, accepting the reality that barrels would wear faster, but calculating that some guns were better than no guns. Molybdenum, which improved steel's high-temperature strength, became almost unobtainable. Japanese sources existed in Korea, but production was limited and transportation was difficult as American submarines tightened their blockade. Engineers substituted vanadium when possible, but it was not as effective. Many gun barrels were manufactured with substandard alloy content, knowing they would have reduced service life, but seeing no alternative given the military's desperate need for weapons. The manufacturing process itself degraded as the war progressed. Skilled workers were conscripted into military service, replaced by hastily trained substitutes who lacked the experience to maintain quality standards. Women and older men filled factory positions, working long hours under difficult conditions. They did their best, but precision metalwork requires experience that cannot be taught in a few weeks of training. Tolerances slipped, inspection procedures were abbreviated to speed production, and defective barrels that would have been rejected in peacetime were accepted because the military needed guns immediately. Electric power shortages affected heat treatment furnaces. The intense Allied bombing campaign against Japanese cities and industrial facilities disrupted power generation and distribution. Furnaces that required precise temperature control often operated on intermittent power, making consistent heat treatment impossible. Metallurgists did what they could, adjusting procedures to work within the constraints, but the results were inevitably inferior to pre-war standards. Testing and quality control, already limited, became luxuries Japan could not afford. Proof testing every barrel was impossible given the ammunition shortages. Visual inspection and basic measurements were all that time and resources permitted. Barrels that might have hidden flaws, microscopic cracks, or areas of improper heat treatment were installed in tanks and artillery pieces because there was no way to identify problems before the guns were put into service. The result was a steady decline in gun barrel life throughout 1944 and into 1945. Tank crews and artillery units reported increasing problems. Barrels wore out faster, requiring more frequent replacement. Accuracy degraded after fewer rounds. In some cases, barrels failed catastrophically during firing, splitting along their length or rupturing at the chamber, killing or injuring the gun crew. Japanese ordnance officers documented these problems in technical reports filed with the Army and Navy technical bureaus. They understood what was happening and why, but understanding the problem and solving it were different matters. Japan's industrial base, stretched to breaking point by 3 years of total war against the world's largest industrial power, simply could not produce high-quality gun barrels in the quantities needed. The empire's metallurgists and engineers did everything possible within their constraints, but those constraints were becoming tighter with each passing month as American forces drew closer to the home islands. The American 75mm gun that Captain Yamamoto examined in August 1945 represented the culmination of decades of American industrial and metallurgical development. The gun was a variant of the M3 tank gun, based on the French 75mm field gun design from World War I, but extensively modified and improved through American engineering and manufacturing processes. Understanding why this gun could fire 12,000 rounds required understanding the entire American system that produced it. American gun barrel manufacturing began with steel of fundamentally higher quality than what Japanese arsenals could obtain. United States Steel Corporation, Bethlehem Steel, Republic Steel, and other major producers operated massive integrated mills that processed iron ore from the Mesabi Range in Minnesota, the richest iron ore deposits in North America. The ore contained 60 to 65% iron by weight, with relatively low impurities. This high-grade ore, combined with modern blast furnaces and steel-making equipment, produced base steel of exceptional consistency. The alloying elements that Japanese metallurgists struggled to obtain were readily available to American manufacturers. Chromium came from domestic mines in Montana and from imports from southern Rhodesia and Turkey, arriving in steady supply throughout the war. Molybdenum came from the Climax mine in Colorado, which produced more than 90% of the world's molybdenum during the war years. Nickel came from Canadian mines in Sudbury, Ontario, shipped across the Great Lakes to American steel mills in quantities that would have seemed fantastic to Japanese planners. American metallurgists specified gun barrel steel, containing approximately 0.4% carbon, 1% chromium, 0.2% molybdenum, and smaller amounts of other elements, including manganese and silicon. These specifications were maintained with remarkable consistency across millions of tons of steel production. The steel mills used electric arc furnaces with precise temperature control and continuous monitoring of chemical composition. Samples were taken throughout the melting process and analyzed using spectroscopic equipment that could detect variations measured in hundredths of a percent. The forging process that shaped raw steel into Datu gun barrel blanks took place at specialized facilities including the Watervliet Arsenal in New York and the Rock Island Arsenal in Illinois. These facilities used hydraulic presses capable of exerting thousands of tons of pressure, forging barrel blanks under controlled conditions that ensured uniform grain structure throughout the steel. The forging was done hot, with the steel heated to approximately 2,300 degrees Fahrenheit, allowing it to flow and compress without cracking while the pressure aligned the steel's internal grain structure along the barrel's length. After forging, the barrel blanks were drilled and reamed to create the bore. This was done on specialized machines that could maintain tolerances of plus or minus 5/10,000ths of an inch across the entire length of the barrel. The rifling was cut using broaching machines that pulled cutting tools through the bore, carving the spiral grooves that would spin the projectile. American arsenals used electrically powered machines with feedback controls that ensured every groove was cut to identical depth and profile. The heat treatment process that followed was critical to the barrel's final performance. American arsenals used electric furnaces with multiple temperature zones, allowing precise control of heating and cooling rates. The barrels were heated to approximately 1,500 degrees Fahrenheit and held at that temperature for several hours, allowing the steel's internal structure to transform. Then they were cooled at carefully controlled rates, sometimes in oil baths, sometimes in air, depending on the specific properties desired. After heat treatment, many American gun barrels received an additional process that was rare in Japanese manufacturing: chrome plating of the bore. A thin layer of hard chromium, typically 2 to 3,000ths of an inch thick, was electroplated onto the rifling and bore surface. This chromium layer was extremely hard, much harder than the underlying steel, and highly resistant to the erosive effects of hot propellant gases. The chrome plating process required specialized equipment and materials, including chromic acid solutions and precise electrical controls, but it dramatically extended barrel life. The final step was proof testing. Every gun barrel manufactured in American arsenals was test-fired with overcharged ammunition, producing pressures exceeding normal service loads. Barrels that showed any signs of weakness, any deviation from specifications, were rejected. The rejection rate was low because the manufacturing process was so well controlled, but it was not zero. American industry could afford to reject imperfect barrels because production capacity was so large that quality took precedence over quantity. The result of this systematic approach was gun barrels of exceptional quality and consistency. When a Sherman tank crew received a new gun barrel, they could rely on it performing to specification for thousands of rounds. Maintenance was straightforward, cleaning after each day's firing and periodic inspection of the bore for wear. Barrel life was predictable, allowing ordnance units to schedule replacements based on round counts rather than unexpected failures. Captain Yamamoto was not the first Japanese metallurgist to examine captured American weapons and reach disturbing conclusions about the disparity in manufacturing quality. Throughout 1944 and into 1945, as American forces advanced across the Pacific and captured increasing quantities of Japanese territory and equipment, Japanese technical intelligence units recovered and analyzed American weapons with growing concern. In December 1944, at the Yokosuka Naval Arsenal, engineers examined a 75mm gun recovered from a Sherman tank destroyed on Peleliu. The tank had been knocked out by a Japanese 47mm anti-tank gun, a rare success for Japanese forces, facing American armor. The crew had been killed, but the gun itself was intact enough for detailed study. The maintenance log found in the tank indicated the barrel had fired approximately 9,300 rounds since installation. The Yokosuka engineers conducted the same examinations Yamamoto would later perform. They measured bore diameter, inspected rifling wear, analyzed the steel's composition and structure. Their report, filed with the Navy Technical Bureau in January 1945, documented what they found: minimal wear, excellent steel quality, evidence of chrome plating in the bore, and manufacturing tolerances far tighter than Japanese arsenals achieved. The engineers estimated the barrel could have fired at least another 3,000 rounds before requiring replacement. At Osaka Army Arsenal in March 1945, ordnance specialists examined multiple American weapons captured on Iwo Jima, including tank guns, artillery pieces, and small arms. They were particularly interested in the M1 Garand rifle, which American infantry carried as standard equipment. The Garand was semi-automatic, firing one round each time the trigger was pulled until its 8-round clip was empty. Japanese infantry still carried bolt-action rifles requiring manual cycling between shots. The examining engineers were impressed by the Garand's mechanical precision. The gas-operated mechanism that cycled the action required tight tolerances and high-quality steel to function reliably. The barrels showed minimal wear despite extensive use. The metallurgical analysis revealed steel quality superior to what Japanese arsenals produced for similar applications. One engineer noted in his report that the Garand represented a level of mass production precision that Japanese industry could not match, that America was apparently manufacturing complex semi-automatic rifles in quantities large enough to equip every infantryman, something Japan had not even attempted. Artillery pieces told the same story. A 105mm howitzer captured on Saipan was examined at Yokosuka in September 1944. The gun had fired an estimated 4,000 rounds, a lifetime's worth of firing for a comparable Japanese gun. The bore showed wear but remained within specifications. The recoil mechanism, a complex hydraulic system requiring precision machining and high-quality seals, functioned perfectly despite months of combat use in tropical conditions. Japanese artillery used similar recoil systems, but they were prone to leaks and failures that required constant maintenance. The accumulating evidence from these examinations pointed to systematic differences in manufacturing capability. American weapons were not just better designed, though many were. They were better made, manufactured to tighter tolerances with better materials and more consistent quality control. The gap was not in one area, but across the entire spectrum of weapons production. Japanese engineers and metallurgists reading these reports understood the implications. If American gun barrels lasted 8 to 10 times longer than Japanese equivalents, American armored units could sustain operations for months without needing replacement barrels. Japanese units needed constant resupply of barrels that Japan's shrinking industrial base could barely provide. If American artillery could fire thousands more rounds before wearing out, American gunners had an enormous sustainability advantage in prolonged combat. The psychological impact on Japanese technical personnel was profound. These were educated men, engineers and scientists who understood metallurgy and manufacturing at a deep level. They had spent years working in Japan's arsenals and laboratories, pushing Japanese industry to its limits to support the war effort. They took professional pride in their work and in Japan's technological achievements. Many had believed Japanese craftsmanship, the traditional emphasis on quality and attention to detail, would compensate for America's quantitative advantages. The captured weapons proved otherwise. American manufacturing was not just larger in scale, it was better in quality. The stereotypes of American products being mass-produced and cheap, widely believed in Japan before the war, were revealed as dangerous misconceptions. American industry combined mass production with precision and quality that Japanese arsenals could not match. The disparity was not just in numbers but in systematic industrial capability at every level, from raw material quality to final inspection procedures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In technical meetings at the Army and Navy ministries in Tokyo during early 1945, these findings were discussed among senior ordnance officers and technical staff. The conversations were somber. Everyone present understood that Japan was fighting an opponent with overwhelming industrial superiority. The question was no longer whether Japan could match American production, that was obviously impossible, but whether Japanese forces could continue fighting effectively with the equipment Japan could actually produce. Captain Yamamoto completed his examination of the American gun barrel on August 21, 1945. His formal report ran to 17 pages, documenting every measurement, every microscopic analysis, every comparison with Japanese equivalents. The technical details were precise and irrefutable. The American barrel had fired 11,800 rounds. Japanese barrels of similar caliber required replacement after 1,500 rounds, sometimes less under combat conditions. The ratio was approximately 8-1, but Yamamoto's report included something beyond technical measurements. In his concluding section, he wrote an analysis that was unusual for a Japanese military document, a frank assessment of what the evidence meant. He noted that the superior barrel life resulted from better steel, better manufacturing processes, better quality control, and the chrome plating process that Japanese arsenals did not use because they lacked the equipment and materials. He noted that every aspect of American gun manufacturing showed evidence of greater industrial capability and systematic attention to quality. Then he wrote something that would have been unthinkable earlier in the war. He stated directly that Japan could not match American metallurgical standards with available resources and industrial capacity. He noted that the gap was widening, not narrowing, as American production continued at high levels, while Japanese production declined under Allied bombing and resource shortages. He concluded that Japanese forces would continue to face opponents with superior equipment that could sustain higher rates of fire for longer periods, giving American units decisive advantages in prolonged combat. The report was filed with the Navy Technical Bureau on August 23, 1945. It was one of thousands of technical reports generated by Japanese arsenals and testing facilities during the war, documenting weapons, analyzing enemy equipment, proposing improvements to Japanese designs. Most of these reports were burned when Japan surrendered on August 15th, destroyed by officers who feared they might be used as evidence in war crimes trials or who simply wanted to eliminate documents that showed Japanese military weaknesses. Yamamoto's report survived, found by American occupation forces in September 1945 when they took control of Yokosuka Arsenal. It was translated by American technical intelligence officers and forwarded to the U.S. Army Ordnance Department and the Aberdeen Proving Ground in Maryland, where American ordnance specialists reviewed it with interest. The report confirmed what American engineers already knew about their own weapons, but provided valuable insight into Japanese metallurgical capabilities and the problems Japanese arsenals faced. For Yamamoto personally, the examination of that gun barrel represented a moment of recognition that went beyond technical analysis. He had devoted his career to Japanese ordnance development, working to improve gun barrels and support Japan's military forces. He had believed that Japanese craftsmanship and engineering skill could overcome material disadvantages. The captured American barrel proved that belief wrong in the most direct way possible. The steel quality, the manufacturing precision, the chrome plating, the consistent performance after thousands of rounds, all demonstrated a level of industrial capability that Japan simply did not possess and could not develop under wartime conditions. American industry could mass-produce weapons of exceptional quality, delivering them to combat units in quantities that seemed unlimited. Japanese industry, strained to the breaking point, could barely maintain production of adequate weapons in insufficient quantities. Yamamoto knew the war was ending. By late August 1945, after the atomic bombings of Hiroshima and Nagasaki and the Soviet invasion of Manchuria, everyone in Japan's military understood that surrender was imminent. His examination of the American gun barrel came in the final days before the formal surrender ceremony on September 2nd. In some ways, the timing made his work pointless, documenting capabilities of an enemy that Japan would no longer fight. But the exercise had value beyond immediate military application. It created a record, a precise technical documentation of the gap between American and Japanese industrial capability in one specific area. That record would inform post-war understanding of why Japan lost, not just in grand strategic terms, but in the concrete details of steel, chemistry, and barrel wear rates and chrome plating processes. The war had been lost not just on battlefields but in factories, in the systematic industrial processes that produced weapons of different quality in vastly different quantities. Yamamoto returned to his laboratory after filing his report. He had other work waiting, other projects that had been ongoing when the American gun barrel arrived for examination. But those projects no longer mattered. The war was ending. Japan had lost. And part of the reason was documented in his report, in the measurements showing that American gun barrels could fire 8 times as many rounds as Japanese equivalents before requiring replacement, a single data point representing the industrial gap that had doomed Japan's war effort from the beginning. The disparity in gun barrel life that Captain Yamamoto documented was not an isolated technical detail. It represented a broader pattern of American industrial superiority that manifested in every aspect of weapons production and military logistics. Understanding why American gun barrels lasted 8 times longer than Japanese equivalents required understanding the entire system that produced them, from iron ore mines in Minnesota to steel mills in Pittsburgh to arsenals in New York, and the economic and industrial foundation that made that system possible. The United States entered World War II with the world's largest industrial economy, producing approximately 40% of global manufacturing output in 1941. American factories had been building automobiles, appliances, and consumer goods in massive quantities throughout the 1920s and 30s, developing mass production techniques and precision manufacturing capabilities that transferred directly to weapons production when war came. The same factories that had built millions of cars could build tens of thousands of tanks. The same machine tools that had manufactured refrigerators could manufacture artillery pieces. American steel production in 1944 reached 89.6 million tons, more than the combined production of Germany, Japan, and Italy. This massive output provided the raw material for weapons, ships, vehicles, and infrastructure. But quantity alone did not explain the quality advantage that Yamamoto's report documented. American steel was not just abundant, it was consistently high quality, because the entire production system, from mining to refining to final manufacture, operated with resources and capabilities that Axis powers could not match. The alloying elements essential for gun barrel steel, chromium, molybdenum, nickel, manganese, were available to American manufacturers in quantities that Japanese engineers could barely imagine. The Climax molybdenum mine in Colorado alone produced more molybdenum during the war than the rest of the world combined. American chromium imports from southern Rhodesia and Turkey arrived on schedule throughout the war, delivered by merchant ships that crossed oceans protected by the U.S. Navy. No submarines threatened American supply lines. No bombers struck American factories. The entire industrial system operated without the disruptions that crippled Japanese production. Quality control in American arsenals reflected this abundance of resources. Inspectors could reject barrels that did not meet specifications because replacement barrels could be manufactured quickly. Proof testing could be done thoroughly because ammunition was plentiful. Chrome plating, which required specialized equipment and materials, was economically feasible because the increased barrel life justified the additional manufacturing cost. Japanese arsenals, struggling with material shortages and desperate production schedules, could not afford such quality measures. The mathematics of sustainability in prolonged combat were brutal. If an American tank battalion, equipped with 76 Sherman, tanks needed to replace gun barrels after 12,000 rounds per gun, and a comparable Japanese tank unit equipped with Type 3 Chi-Nu tanks needed replacements after 1,500 rounds per gun, the American unit could sustain 8 times as much firing before requiring the same level of logistical support. In a campaign lasting months, where tanks might fire hundreds of rounds in a single day during heavy combat, this difference meant American armor could maintain combat effectiveness, while Japanese armor degraded and eventually became non-operational as barrels wore out and replacements were unavailable. Artillery told the same story at larger scale. American 105mm howitzers, standard divisional artillery throughout the U.S. Army, could fire approximately 10,000 rounds before requiring barrel replacement. Japanese equivalent artillery, the Type 91 105mm howitzer, required new barrels after approximately 2,000 rounds. American artillery units could sustain much higher rates of fire for much longer periods, providing infantry with overwhelming fire support that Japanese forces could not match. The cumulative effect across thousands of weapons and millions of rounds was decisive. American forces could fight prolonged battles with sustained firepower. Japanese forces, even when they had ammunition available, faced declining weapon performance as barrels wore out. Gun crews learned to compensate for decreased accuracy as rifling wore smooth, but compensation had limits. Eventually, worn barrels became dangerous to their own crews, prone to ruptures and explosions. Japanese ordnance units documented these problems in reports filed throughout 1944 and 1945. Tank battalions reported gun barrels wearing out faster than replacements could be supplied. Artillery regiments requested new barrels that arsenals could not manufacture quickly enough. Recommendations were made to reduce firing rates to extend barrel life, but reduced firing rates meant less effective fire support and greater casualties among infantry who depended on artillery and tank support. The problem had no solution within Japan's industrial capabilities. Manufacturing better gun barrels required better steel, which required alloying elements Japan could not obtain in sufficient quantities. It required better manufacturing equipment, which Japan could not build because the same factories that might have produced improved machine tools were committed to producing weapons. It required electric power for heat treatment furnaces, but power generation was declining as American bombers destroyed generating plants and distribution systems. When American occupation forces arrived in Japan in September 1945, technical intelligence teams fanned out across the country to assess Japanese industrial capabilities and gather information about weapons development, production. Officers from the U.S. Army Ordnance Department, the Navy Bureau of Ordnance, and the Army Air Forces visited arsenals, laboratories, and manufacturing facilities that had supported Japan's war effort. What they found confirmed and expanded the understanding that had been developing through examination of captured weapons throughout the war. At Yokosuka Naval Arsenal, American engineers found Yamamoto's report and dozens of similar technical studies documenting Japanese analysis of captured American weapons. The reports showed that Japanese technical personnel had understood their disadvantages clearly and had attempted to find solutions within their resource constraints. They had experimented with alternative alloying elements, modified heat treatment procedures to work with lower quality steel, and developed maintenance procedures to extend barrel life. But none of these efforts could overcome the fundamental gap in industrial capability. The American teams examined Japanese gun barrel manufacturing facilities and documented the equipment and processes used. The facilities were well designed, and the equipment was generally comparable to what American arsenals had used in the 1920s and early 1930s. But they lacked the modern, electrically controlled furnaces that American arsenals had installed in the late 1930s. They lacked the precision machine tools that American facilities used for boring and rifling. They lacked the chrome plating equipment that extended American barrel life. Most significantly, they lacked consistent access to high-quality steel with proper alloying elements. Japanese metallurgists, interviewed by American teams, were candid about the problems they had faced. They described the progressive degradation of steel quality as the war continued and material shortages worsened. They explained how specifications had been relaxed to maintain production even though everyone knew the resulting gun barrels would have reduced service life. They discussed the impossible choices between quality and quantity, knowing that substandard weapons were better than no weapons, but understanding that substandard weapons meant higher casualties among Japanese forces using them. One senior engineer at Osaka Arsenal told American interviewers that by 1945, Japanese gun barrel steel contained approximately one-third the chromium content that specifications called for and virtually no molybdenum. Heat treatment was done with whatever electric power was available, sometimes with inadequate temperature control because power shortages forced furnaces to operate on reduced voltage. Quality control had been reduced to visual inspection because proof testing consumed ammunition that was desperately needed for combat. He estimated that gun barrels manufactured in the final year of the war had perhaps half the service life of barrels manufactured in 1942, and those earlier, barrels were already inferior to American equivalents. The technical intelligence reports compiled from these visits provided detailed documentation of Japanese industrial weaknesses. They confirmed what combat experience had already demonstrated, that Japanese weapons, while adequate in design and in many cases cleverly engineered to work within resource constraints, were manufactured with materials and processes that produced inferior performance compared to American equivalents. The gap was not in engineering knowledge, but in industrial capability, in the systematic differences between an economy with abundant resources and modern equipment versus an economy strained by years of war and cut off from essential materials. These reports informed post-war American understanding of the Pacific War's industrial dimension. Military historians and strategists studying why Japan lost identified numerous factors. Strategic errors in provoking American entry into the war, the decision to attack Pearl Harbor, tactical mistakes in various campaigns, the failure to develop adequate anti-submarine warfare capabilities that allowed American submarines to devastate Japanese merchant shipping. But underlying all these factors was the industrial disparity that made prolonged war unwinnable for Japan regardless of strategy or tactics. The gun barrel life disparity that Yamamoto documented became a standard example in post-war analysis of industrial warfare. It appeared in U.S. Army studies of logistics and sustainability in combat operations. It was cited in metallurgical engineering courses discussing the importance of material quality in weapons manufacture. It became part of the historical record documenting how industrial capacity influenced military outcomes in World War II. For Japanese engineers and metallurgists working to rebuild Japan's industrial base after the war, the lessons were painful but clear. Quality required not just knowledge and skill, but access to both proper materials and equipment. Mass production required not just factories but the entire supporting infrastructure of power generation, transportation, raw material supply, and skilled workforce. Building an industrial economy capable of competing with advanced Western nations required decades of investment in education, infrastructure, and technology. Japan's post-war industrial development benefited from American occupation policies that emphasized economic reconstruction and from access to American technology and manufacturing techniques. By the 1960s and 70s, Japanese industry had not only recovered, but had become globally competitive in many sectors, including steel production and precision manufacturing. But that achievement came after 20 years of rebuilding and required peace, stability, access to global markets and resources, and the opportunity to learn from more advanced industrial nations without the pressure of wartime production demands. The technical story of gun barrel life, measured in rounds fired and steel composition and chrome plating processes, represented human stories of soldiers fighting with inadequate equipment and understanding too late that their weapons could not sustain prolonged combat. Japanese tank crews, artillery gunners, and infantry using worn-out weapons faced American forces equipped with guns that functioned reliably after thousands of rounds. The disparity was not abstract statistics, but concrete battlefield reality that cost lives and determined outcomes. A Japanese tank company commander on Okinawa, interviewed after his capture in June 1945, described how his Type 3 Chi-Nu tanks, the most modern Japanese tanks available, had experienced gun barrel problems during the fighting. The tanks mounted 75mm guns, the best anti-tank weapons Japanese armor possessed. But after several days of combat, with the tanks firing dozens of rounds daily against American positions and vehicles, the gun barrels began showing significant wear. Accuracy declined. The rifling was wearing smooth, causing rounds to tumble rather than fly straight. One gun barrel split along its length during firing, fortunately without injuring the crew but rendering the tank's main armament useless. The commander had requested replacement barrels from the regimental supply officer. He was told that no replacements were available on Okinawa and that none could be shipped from Japan because American naval and air forces controlled all approaches to the island. His tanks would have to continue fighting with worn barrels or be abandoned. He chose to continue fighting, knowing his guns were increasingly ineffective, because abandoning the tanks meant his crews would become infantry without proper infantry training or equipment. His company lost all its tanks within 2 weeks, destroyed by American Shermans, whose guns functioned perfectly, and by infantry using bazookas and demolition charges against armor that was inadequate from the beginning. Artillery units faced similar problems on a larger scale. Japanese artillery on Iwo Jima, dug into caves and fortified positions, provided fierce resistance to American forces landing in February 1945. But the intense firing rates required to interdict American landing beaches and counter American artillery meant gun barrels wore out quickly. After a week of combat, many Japanese guns showed serious accuracy problems. Some barrels split or ruptured, killing gun crews. American counter-battery fire, directed by spotter aircraft and ground observers, systematically destroyed Japanese artillery positions. But even guns that survived American fire often became ineffective, as worn barrels could no longer deliver accurate fire. The contrast with American artillery was stark. American 105mm and 155mm howitzers fired thousands of rounds, supporting the Iwo Jima assault. Barrels remained within specifications. When barrels did wear out, replacements were available from supply ships offshore. American artillery could sustain high firing rates throughout the month-long battle, providing continuous support to infantry advancing against fortified Japanese positions. Japanese artillery, even when it survived American counter-battery fire, declined in effectiveness as barrels wore out and could not be replaced. For Japanese ordnance officers and technical personnel who understood the reasons for these problems, the experience was professionally and personally devastating. They had worked for years to support Japanese military forces, designing weapons, improving manufacturing processes, solving technical problems within severe resource constraints. They had done everything possible with what they had. It was not enough. American industrial superiority was too great, manifesting not in dramatic technological breakthroughs but in systematic quality advantages across thousands of weapons and millions of rounds of ammunition. The gun barrel life disparity was one example among many. American aircraft engines lasted longer between overhauls. American vehicles required less maintenance. American radios functioned more reliably. American optical equipment provided clearer views. In every category of military equipment, American weapons showed consistent quality advantages resulting from better materials, better manufacturing equipment, and better quality control. The cumulative effect was overwhelming. Captain Yamamoto's report, documenting that American 75mm gun barrels could fire 12,000 rounds, while Japanese equivalents required replacement after 1,500 rounds, told a story that extended far beyond one gun barrel examined in one laboratory in August 1945. It told the story of how industrial capacity determined military outcomes in modern warfare, how factories and steel mills were as important as battlefields, how the nation that could produce better weapons in larger quantities had decisive advantages that strategy and tactics and fighting spirit could not overcome. The Japanese metallurgists who examined captured American weapons during the war, who documented the quality of American steel and the precision of American manufacturing, understood this truth before Japan's military leadership fully accepted it. They saw in microscopic photographs of steel grain structure and in measurements of bore diameter the evidence of industrial capabilities Japan could not match. They knew, months before the atomic bombs and the Soviet invasion and the final surrender, that Japan had been fighting a war it could not win because the industrial foundation was too weak. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.